Hello, sleepy genius. Another day has passed, and now it's time to let go. Your mind has worked hard, carried weight, solved problems. Tonight, we'll travel somewhere impossible together. A place where gravity bends, where light takes new forms, where our familiar star becomes something else entirely. Let yourself sink into this journey. You're safe here. From the moment our sun first ignited 4.6 billion years ago to the countless other cosmic furnaces scattered across the void, our star has been the quiet architect of everything we know. But what if we could reach into the cosmos and swap it out? What strange new worlds would emerge under different lights? Tonight, we'll replace our sun with the universe's most extraordinary objects, one by one, and watch what happens to Earth. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please, share your thoughts below. Now, let's begin. If we swapped our sun with Venus, Earth would circle a scorching sphere wrapped in acid clouds and crushing atmosphere. Imagine looking up to see not a bright disk, but a pale yellow orb veiled in sulfuric haze, casting a sickly, diffused glow across the land. Venus measures 12,104 kilometers wide, just 650 kilometers smaller than Earth, and rotates so slowly that one Venusian day equals 243 Earth days, making it the slowest rotating planet discovered. Surface temperatures reach 465 degrees Celsius, hot enough to melt lead, sustained by a runaway greenhouse effect that trapped carbon dioxide over millions of years. Soviet Venera landers in the 1970s survived mere hours before the heat and pressure crushed their titanium hulls. This reminds us that proximity alone does not guarantee kinship. Our nearest neighbor is an inferno of cautionary tales. If we replaced our sun with Proxima Centauri, Earth would plunge into an eternal twilight. Picture standing outside at what should be noon, but the sky glows only as bright as a full moon night, casting long shadows that never quite disappear, everything bathed in deep red, like an old photograph left in sunlight. Proxima Centauri is a red dwarf star located 4.24 light-years away, measuring just 14% the mass of our sun and shining with only 0.0017 times its luminosity. Discovered in 1915 by astronomer Robert Innes at the Union Observatory in South Africa, this tiny star burns at a surface temperature of merely 3,000 Kelvin compared to our sun's 5,778 Kelvin. Without proper greenhouse warming, Earth's oceans would freeze solid within weeks, encasing our planet in ice kilometers thick. To think that the nearest star to our solar system would turn our world into a frozen wasteland, a reminder that proximity means nothing without the right light. If Jupiter replaced the sun, Earth would be crushed by tidal forces before we even noticed the cold. Picture standing on a beach as the ocean rises, not in slow tides but in towering walls, kilometers high, pulled upward by impossible gravitational forces. Jupiter has a mass 318 times that of Earth, but still only 0.001 times the mass of the Sun. It radiates more heat than it receives, about 1.6 times more, due to gravitational contraction. Observations from NASA's Juno spacecraft, which entered orbit in 2016, reveal wind speeds exceeding 600 kilometers per hour and a great red spot storm larger than Earth that has raged for at least 350 years. But Jupiter emits mostly infrared radiation, invisible to human eyes. We would see only a dull reddish sphere, faintly glowing, before tidal forces shattered tectonic plates and boiled the oceans into steam. To think that even the largest planet in our solar system is a mere ember compared to the furnace we orbit. If we swapped our sun with Sirius, the brightest star in our night sky, Earth would become a furnace. Imagine waking to a sun so brilliant it hurts to look anywhere near it. The sky washed white with light, shadows sharp as cut glass, the air shimmering with heat even at dawn. Sirius A burns 25 times more luminously than our sun and sits 8.6 light-years away in the constellation Canis Major. This blue-white star, known to ancient Egyptians who called it Sopdat and built their calendar around its rising, radiates at 9,940 Kelvin. Within days, Earth's surface temperature would climb past 100 degrees Celsius, boiling away oceans and stripping the atmosphere as water vapor escaped into space. Astronomers Friedrich Bessel discovered in 1844 that Sirius wobbles, revealing it has a white dwarf companion, Sirius B, orbiting every 50 years. This reminds us that brightness is a kind of violence, that some lights are too fierce for life to hide beneath. If we placed Betelgeuse where our sun sits, it would swallow Earth whole. Picture looking up to see not a point of light, but a vast red wall filling half the sky, its surface roiling with storms larger than our entire orbit, close enough to feel its heat as radiation prickling your skin. Betelgeuse is a red supergiant in Orion's shoulder, measuring 764 times wider than our Sun, large enough that if centered on our solar system, it would extend past Jupiter's orbit. Discovered to be variable in brightness by astronomer John Herschel in 1836, this dying star sits 548 light-years away and shines 140,000 times more luminously than our Sun. Earth would vaporize instantly, its atoms scattered into the stellar wind that Betelgeuse sheds at a rate equal to 1 Earth mass every 400 years. To think that this star, visible as a steady orange point on winter nights, is actually a cosmic monster counting down to supernova, perhaps within the next 100,000 years. If Neptune replaced our Sun, we would be plunged into a darkness, lit only by the fastest winds in the solar system. Imagine staring up at a deep blue sphere, darker than a sapphire, where storms rage at 2,100 kilometers per hour, the fastest planetary winds ever recorded. Neptune radiates 2.6 times more heat than it receives, the most of any planet, likely due to residual heat from its formation 4.5 billion years ago. Voyager 2 visited Neptune in 1989, capturing images of the Great Dark Spot, a storm system the size of Earth that has since disappeared. Neptune's blue color comes from methane in its atmosphere, which absorbs red light. But without the Sun, that blue would be invisible, and Earth would spiral into temperatures below -220 degrees Celsius. This reminds us that internal heat is not the same as starlight, that even the most energetic planets are dim candles compared to the Sun. If we replaced our Sun with a neutron star, Earth would be torn apart before we even noticed the light. Imagine gravity suddenly multiplying 1 billion times, your body crushed flat in an instant, the ground beneath you spaghettified and pulled upward in streams, the atmosphere compressed into a thin shell of superheated plasma. Neutron stars are the collapsed cores of massive stars, typically 20 kilometers in diameter but containing 1 times the Sun's mass, creating surface gravity 200 billion times stronger than Earth's. First theorized by Walter Bod and Fritz Zwicky in 1934, and confirmed when Jocelyn Bell Burnell discovered pulsars in 1967. These objects spin up to 716 times per second while radiating across all wavelengths. At the distance of our Sun, a neutron star would tidally disrupt Earth within seconds, stretching and compressing it until the planet shattered into a ring of debris spiraling inward. In a sense, we owe our existence to being the right distance from the right kind of star, a balance so precise that most cosmic objects would undo us instantly. If we swapped our sun with a black hole of equal mass, Earth would survive in perpetual darkness. Picture the solar system continuing its orbit around nothing visible, just empty space where light used to pour from. The stars now scattered across a completely black sky, no dawn ever breaking again. A solar mass black hole would measure only 6 kilometers across at its event horizon. As calculated by Carl Schwarzschild in 1916 using Einstein's field equations just months after general relativity was published. Without sunlight, photosynthesis would cease immediately, and Earth's surface temperature would plummet to -240 degrees Celsius within a week as thermal radiation bled into space. The gravitational pull would remain identical to our Sun since mass determines orbital mechanics, not luminosity, so our year would still last 365 days around this invisible monster. Astronomers now believe supermassive black holes lurk at the center of most galaxies, including Sagittarius A star in our Milky Way, discovered in 1974 by Bruce Ballack and Robert Brown. This reminds us that light is a gift, not a given, that gravity alone cannot sustain the fragile chemistry we call life. If we replaced our Sun with Canis Majoris, one of the largest known stars, it would engulf everything out to Saturn's orbit. Imagine standing on Earth as a red cloud of plasma closes in from all sides. The star's outer layers so diffuse you could see through them to scattered starlight beyond, but hot enough to melt rock, the planet dissolving like a sugar cube in hot tea. Canis Majoris stretches roughly 1,420 times wider than our Sun, measuring approximately 2 billion kilometers in diameter. Located 3,840 light-years away in Canis Major, this red hypergiant was first catalogued in 1801 by French astronomer Jérôme Lalande, but its true size wasn't understood until infrared observations in the 1990s. The star sheds mass so rapidly through stellar wind that it's surrounded by a nebula of ejected material weighing several times the mass of Jupiter. To think that stars can grow so large they begin to tear themselves apart. Beauty and destruction happening simultaneously in slow cosmic time. If we swapped our Sun with a white dwarf, Earth would freeze but remain intact. Picture a Sun shrunk to the size of Earth itself, glowing dull white like a dying ember, casting barely enough light to read by even at noon, the sky a perpetual deep blue twilight. White dwarfs are the remnants of stars like our Sun after they've shed their outer layers, packing about half a solar mass into a sphere roughly 12,000 kilometers across, with density so extreme that a teaspoon would weigh 15 tons on Earth. First discovered in 1862 when Alvin Graham Clark spotted Sirius B while testing a new telescope. These stellar corpses shine only from leftover heat, no fusion occurring in their carbon-oxygen cores. Without a fusion furnace generating light, Earth's temperature would drop to -200 Celsius, creating an ice world orbiting a ghostly cinder that will glow for trillions of years before finally going dark. In a sense, this is our Sun's destiny, written in the physics of stellar evolution. A future Earth 5 billion years from now, when the light finally fades. If we placed a magnetar where our Sun sits, Earth would be sterilized by radiation within seconds. Imagine a pulse of X-rays and gamma rays so intense it ionizes the atmosphere instantly, stripping electrons from every atom. the magnetic field warping space itself so powerfully that atoms elongate into needle shapes. Your very matter restructured before consciousness ends. Magnetars are neutron stars with magnetic fields measuring up to 100 billion Tesla, 1,000 trillion times stronger than Earth's field and 1,000 times more powerful than typical neutron stars. Discovered in 1998 when astronomer Krisa Kuvaliotu identified SGR 180620 as having an unusually strong magnetic field, these objects experience starquakes that release more energy in 1/10 of a second than our Sun emits in 100,000 years. The magnetar's field would interact with Earth's iron core, potentially reversing our planet's rotation or ripping apart our magnetic shield entirely. This reminds us that the universe contains forces so extreme they defy comfortable understanding, that our survival depends on cosmic neighbors being safely distant. If we replaced our Sun with the quasar 3C 273, Earth would cease to exist as matter. Picture not death, but conversion. Every atom in your body struck by such intense radiation, it transforms into pure energy. The planet not melting but dissociating, the very electrons stripped away, leaving only a cloud of naked nuclei screaming outward at a fraction of light speed. Quasar 3C 273 sits 2.5 billion light-years away in Virgo. Discovered in 1963 by astronomer Martin Schmidt, who realized its redshift meant impossible distance and luminosity. This supermassive black hole, actively feeding on infalling matter, shines 4 trillion times brighter than our Sun, radiating more energy in 1 second than our Sun produces in 400 years. At 1 astronomical unit, the radiation pressure alone would exceed gravity, meaning Earth would be pushed outward while simultaneously being torn apart by tidal forces and irradiated into plasma. To think that these objects existed when the universe was young, that we see them as they were billions of years ago, ancient lighthouses in the cosmic dark. If we swapped our Sun with a brown dwarf, Earth would enter a dim red twilight, barely distinguishing day from night. Imagine a Sun that failed, too small to ignite true fusion, glowing only from gravitational compression heat, casting just enough light to see your hand if you held it close, the world a place of permanent dusk. Brown dwarfs straddle the boundary between planets and stars, typically ranging from 13 to 80 Jupiter masses. Discovered first in 1995 when astronomers at Caltech identified Gliese 229b using adaptive optics. These failed stars burned deuterium briefly but never achieved the core temperatures needed for hydrogen fusion, instead cooling slowly over billions of years like cosmic embers. Earth's surface temperature under a brown dwarf would plummet to -150 Celsius, creating a frozen world where only extremophile bacteria might survive in geothermal pockets near volcanic vents. In a sense, brown dwarfs represent the universe's most common missed opportunity, countless almost stars scattered through the galaxy. Neither planet nor Sun, but something in between. If we placed a pulsar where our Sun sits, Earth would be swept by a lighthouse beam of deadly radiation thousands of times per second. Picture reality flickering, each pulse a strobe of gamma rays cooking the atmosphere, creating cascades of secondary particles. The magnetic field so intense, it induces currents in Earth's core strong enough to melt rock. The planet beginning to glow red from electromagnetic induction heating. Pulsars are rotating neutron stars with beams of radiation emanating from their magnetic poles, spinning between once per second to 716 rotations per second in the case of Jones 7482446, discovered in 2004. Jocelyn Bell Bernal first detected pulsars in 1967 telescope at Cambridge, initially wondering if the precise 1.337-second pulses might be artificial signals from extraterrestrial intelligence. The pulsar wind, a stream of charged particles flowing outward at nearly light speed, would strip Earth's atmosphere in days, while the intense radiation field destroyed all biological molecules. This reminds us that the universe recycles matter in violent ways, that stellar death creates some of the most extreme physics possible. If we swapped our sun with a T-Tauri star, Earth would be bombarded by stellar winds strong enough to erode mountains. Imagine standing under a sun that's still being born, its light flickering wildly, massive solar flares erupting every few hours, each one releasing more energy than 1,000,000 atomic bombs. The sky filled with auroras that never fade, stretching from pole to pole. T-Tauri stars are infant suns less than 10 million years old, still contracting under gravity and clearing away their birth nebula through powerful magnetic activity. First discovered by astronomer John Russell Hind in 1852, these young stars lose mass through stellar winds at rates up to 100 billion times stronger than our current sun's solar wind. Earth's magnetic field would be continuously compressed and breached, allowing charged particles to reach the surface and strip away atmosphere at a rate of several tons per second. To think that our sun passed through this violent adolescence 4.6 billion years ago, that all stars begin as chaos before settling into steady fusion, makes our current calm seem like a temporary grace. If we replaced our sun with a blue supergiant like Rigel, Earth would be flooded with ultraviolet radiation intense enough to break chemical bonds. Picture a sun so hot it glows blue-white, its light harsh and clinical, shadows absolutely black by contrast. The ozone layer shredded within hours. Every living cell's DNA snipped apart by UV photons, mutations cascading faster than repair mechanisms can function. Rigel burns at approximately 11,000 Kelvin and radiates 120,000 times more luminously than our sun from a distance of 860 light-years in the constellation Orion. Discovered to be a quadruple star system through spectroscopy by Frank Schlesinger in 1920, Rigel's primary star alone outshines our sun by a factor that would raise Earth's surface temperature to over 300 Celsius within days. The intense stellar wind, carrying mass away at millions of kilometers per hour, would interact with Earth's magnetosphere and create radiation belts 1,000 times more dangerous than Jupiter's, in a sense. These massive blue stars live fast and die young, burning through their fuel in mere millions of years, where our sun will shine for 10 billion. A reminder that brightness costs dearly. If we swapped our sun with Wolf-Rayet's star WR104, Earth would be caught in the spiral of stellar wind preceding a supernova. Imagine looking up to see a vast pinwheel pattern in the sky, streams of matter spinning outward in a cosmic spiral. The star at the center shedding mass so rapidly you can see new material ejected every 8 hours. The whole structure glowing in infrared from dust grains condensing out of the wind. Wolf-Rayet stars are massive stars near the end of their lives, stripped of their outer hydrogen layers to reveal helium and heavier elements burning at their cores. First discovered by Charles Wolfe and Georges Rayet in 1867 while observing 3 stars in Cygnus with unusual emission lines. WR104 sits 2,580 light-years away and forms a spiral nebula with its binary companion, creating a dust pinwheel that rotates every 241 days. If placed at our sun's distance, Earth would be immersed in stellar wind containing carbon, oxygen, and iron atoms moving at 2,000 kilometers per second, scattering and irradiating anything in its path. This reminds us that stars die elaborately, that their final centuries are spent casting off layers like cosmic veils, preparing for the moment when core collapse triggers supernova. If we placed a carbon star where our sun sits, Earth would be shrouded in soot. Picture a sun glowing deep red, surrounded by clouds of carbon particles it's continuously ejecting. The sky darkening to a rusty haze as graphite dust accumulates in the upper atmosphere, settling slowly like black snow that coats everything. Photosynthesis blocked by a veil of stellar ash. Carbon stars form when dying red giants dredge up carbon from their cores through convection, creating more carbon than oxygen in their atmospheres, which allows carbon molecules to form and condense into dust grains. First recognized as a distinct class by astronomer Angelo Secchi in 1868. These stars, like our Sculptris, shed dust at rates that create entire shells of material visible in infrared telescopes. At 1 astronomical unit, this carbon production would fill Earth's orbital space with enough fine particles to drop sunlight levels below the threshold needed for plant life, while the star's cool temperature of around 3000 Kelvin would freeze our oceans. To think that carbon, the element of life on Earth, becomes an agent of darkness when overproduced, illustrates how balance determines habitability. If we swapped our sun with a Cepheid variable star, Earth would experience seasons of fire and ice every few days. Imagine a sun that pulses like a beating heart, swelling brighter over 3 days until it blazes twice as hot, then dimming again over 3 more days. The temperature cycling wildly, ice forming at night, melting by noon. Weather patterns thrown into chaos by the constantly changing energy input. Cepheid variables are supergiant stars that expand and contract regularly. Discovered by John Goodricke in 1784 when he noticed Delta Cephei brightening and dimming every 5.4 days. Henrietta Swan Leavitt's 1912 discovery that Cepheid periods correlate with their intrinsic luminosity made them the cosmic yardsticks that revealed the battery universe's true scale. A Cepheid at our sun's position would vary in luminosity by a factor of 2 to 10, causing Earth's surface temperature to swing by hundreds of degrees Celsius with each pulse, making stable climate and therefore complex life completely impossible. In a sense, we're fortunate to orbit a main sequence star whose fusion rate stays nearly constant, a cosmic metronome reliable enough that life could adapt to its rhythm. If we replaced our sun with a red giant in helium flash, Earth would be briefly illuminated by the brightest light in the solar system's history. Picture our sun suddenly exploding outward, not as a supernova but as an expansion event. Its core igniting helium fusion all at once, releasing in seconds what normally takes years. The light intensifying until it hurts, a false dawn of apocalyptic brightness. Helium flash occurs in stars of our sun's mass when their cores reach 100 million Kelvin, and degenerate matter suddenly ignites all its helium at once, releasing about 100 billion times the sun's normal luminosity for a few seconds before stabilizing. First predicted by physicist Fred Hoyle in 1959 and confirmed through stellar models, this event happens buried deep inside the star, so we'd never see it directly. But if exposed at our distance, the radiation would vaporize Earth's surface rock within moments. The helium flash represents a star's desperate transition from hydrogen to helium burning, a violent reconfiguration of its power source. This reminds us that even stable stars have moments of transformation. That change in the universe often comes in dramatic bursts between long periods of steady state. If we swapped our sun with a flare star like UV Ceti, Earth would be hit by radiation storms hundreds of times stronger than any solar flare we've experienced. Imagine the sky suddenly brightening as the star releases a flare equal to 10% of its total luminosity. Lasting minutes to hours, the magnetic field lines on Earth compressing violently, power grids overloading, auroras visible at the equator. The atmosphere heating and expanding as it absorbs UV Ceti, discovered in 1948 by Willem Leighton, is a red dwarf just 8.7 light-years away that undergoes flares, increasing its brightness by up to 5 times normal levels, unpredictably. These flares result from magnetic reconnection events similar to solar flares, but proportionally much more powerful relative to the star's base luminosity. At our sun's distance, such flares would strip away Earth's ozone layer repeatedly, dose the surface with sterilizing radiation, and potentially erode the atmosphere entirely over geologic time. To think that the most common stars in our galaxy, the red dwarfs that make up 75% of all stars, are also the most temperamental and violent illustrates how rare our gentle yellow star truly is. If we placed a luminous blue variable like Eta Carinae where our sun sits, Earth would be incinerated by a star actively destroying itself. Imagine a sun so massive and unstable it sheds mass equivalent to Earth every month through eruptions and stellar wind, the sky filled with expanding shells of gas from previous outbursts, the star's luminosity jumping erratically between 1 million and 5 million times our sun's output. Eta Carinae sits 7,500 light-years away in the southern constellation Carina, famous for its great eruption between 1837 and 1856, when it briefly became the second brightest star in the night sky despite its enormous distance. Astronomers now know it's a binary system with the primary star weighing over 100 solar masses, approaching the theoretical maximum mass for stars. At 1 astronomical unit, the intense radiation would heat Earth's surface to thousands of degrees within hours, vaporizing oceans and atmosphere alike, while the powerful stellar wind would push against our planet with physical force measurable in tons per square meter. In a sense, these massive stars are cosmic accidents, too large to be stable, living only a few million years before exploding as supernova, their brightness a symptom of terminal instability. If we swapped our sun with a planetary nebula's central star, Earth would orbit a white dwarf surrounded by the glowing ghost of its former self. Picture a tiny, brilliant point of light, no larger than Earth, but blazing at 100,000 Kelvin, surrounded by an expanding shell of multicolored gas, lit from within like a cosmic lamp. Greens from oxygen, reds from hydrogen, blues from helium, the nebula growing larger each year as it drifts away at 20 kilometers per second. Planetary nebulae form when red giant stars shed their outer layers in relatively gentle stellar winds, revealing the hot core beneath, first catalogued by Charles Messier in the 18th century, who called them planetary nebulae because, through his telescope, they looked like the pale disks of Uranus or Neptune. The central white dwarf radiates primarily in ultraviolet light, intense, enough to ionize the expanding gas, but without enough total energy to warm Earth above -180 Celsius, creating a frozen world bathed in eerie nebular glow from all directions. This reminds us that stellar death can be beautiful, that stars end not always in violence, but sometimes in a slow unfurling of their substance into space, returning their matter to the cosmos. If we replaced our sun with a symbiotic binary like our query Earth, would orbit 2 stars simultaneously destroying and creating each other. Imagine a red giant shedding matter that falls onto a nearby white dwarf. The dwarf's surface accumulating hydrogen until it reaches critical density and ignites in a thermonuclear explosion called a nova, the blast wave hitting the red giant and stripping away more of its outer layers, the cycle repeating every several decades. Our Aquarii sits 710 light-years away and was discovered to be variable by Carl Ludwig Harding in 1810. But its binary nature wasn't understood until spectroscopy revealed two distinct stellar components. The system undergoes nova eruptions approximately every 44 years, each explosion ejecting matter at 6,000 kilometers per second and creating intricate nebula, structures visible in Hubble telescope images. If positioned at our sun's distance, Earth would be periodically swept by nova blast waves, each one delivering radiation and particle bombardment that would sterilize the surface, while the gravitational interaction of two stellar masses might perturb our orbit unpredictably. To think that stars can be locked in such violent partnerships, feeding and destroying each other in slow motion over millennia, reveals how dynamic stellar evolution can be. If we swapped our sun with a red supergiant in its death throes like Antares, Earth would be engulfed by a star actively preparing for supernova. Imagine a sun that fills the sky from horizon to horizon to horizon, its surface close enough to see individual convection cells larger than Jupiter churning and bubbling, giant plumes of plasma rising and falling over weeks. The light dim red, but the heat overwhelming as Earth spirals through the star's outer atmosphere. Antares, in Scorpius, measures about 680 times wider than our Sun and shines 57,500 times more luminously from 550 light-years away, discovered to be binary through lunar occultation measurements in 1819 by Scottish astronomer James William Grant. The star's density is so low that its outer layers qualify as a laboratory vacuum by Earth standards, yet it contains 12 solar masses total. Within this tenuous but vast atmosphere, Earth would experience drag forces that circularize its orbit while friction heat vaporizes the surface, the planet essentially burning up like a meteor in stellar material. In a sense, this is a preview of Earth's eventual fate when our own sun becomes a red giant in 5 billion years, though we'll be consumed from the inside of the expansion rather than being imported into an already giant star. If we placed a contact binary like WRC Majoris where our sun sits, Earth would orbit two stars so close they share an atmosphere. Picture twin suns touching, their surfaces merging in a bridge of plasma, matter flowing between them, the combined shape resembling a peanut or hourglass, spinning end over end every few hours, the light pulsing as we alternately see one star and then the other eclipsing it from our viewpoint. WRC Majoris type systems consist of two main sequence stars orbiting so closely that their outer layers merge into a common envelope. First discovered by German astronomer Friedrich August Theodor Winnig in 1867, the stars orbit their common center of mass in periods typically ranging from 5 to 14 hours, locked in gravitational embrace so tight that tidal forces have synchronized their rotation and stretched them into egg shapes. At our sun's distance, Earth would experience complex gravitational perturbations from two stellar masses orbiting each other, potentially destabilizing our orbit over millions of years, while the variable light output as the stars eclipse each other would create bizarre daily temperature cycles. This reminds us that binary stars are actually more common in the universe than solitary stars like our Sun, that we're the unusual case, orbiting alone. If we swapped our Sun with a Wolf-Rayet binary like WR140, Earth would be caught between two massive stars spiraling toward merger. Imagine dual suns racing around each other every 7.94 years in an elliptical orbit. One star shedding powerful stellar wind, the other star's wind colliding with the first, creating a shock front visible in infrared as a spiraling dust pattern, each periastron passage releasing enormous amounts of energy, the combined radiation varying wildly throughout their orbit. WR140 consists of a Wolf-Rayet star and an O-type supergiant separated by less than the distance from Earth to Saturn at their closest approach, discovered through its peculiar dust production cycle by astronomers in the 1970s. When the stars come closest together every 8 years, their stellar winds collide at relative velocities of 3,000 kilometers per second, creating dust that forms a pinwheel pattern as it cools and is blown outward by radiation pressure. Earth caught in this system would be alternately baked by dual radiation and swept by colliding stellar winds, the environment changing dramatically over the course of the orbit in ways that would prevent any stable climate. To think that massive stars can orbit each other in such tight, deadly dances, their winds clashing like cosmic storms, illustrates how violent the universe is at stellar scales. If we replaced our Sun with the supermassive black hole Sagittarius A star at the Milky Way's center, Earth would orbit in a region filled with other stars and intense radiation. Imagine darkness where the Sun should be, but the sky blazing with stars packed thousands of times more densely than our neighborhood, and at the center, a precise point of absolute black, surrounded by a disk of superheated gas spiraling inward, glowing in X-rays as matter accelerates to relativistic speeds before disappearing forever. Sagittarius A star weighs 1 million solar masses compressed into a region smaller than Mercury's orbit. Discovered in 1974 as a bright radio source and confirmed as a black hole through observations by Andrea Ghez and Reinhard Genzel, tracking stars orbiting at speeds up to 5,000 kilometers per second. At 1 astronomical unit from this monster, Earth would complete an orbit in just 15 days rather than a year. The tidal forces stretching and compressing our planet by meters with each orbit, while the accretion disk's radiation would be filtered by intervening material but still problematically intense. In a sense, black holes prove that matter can achieve states of compression so extreme that space-time itself breaks down, that the universe contains pockets where our physics equations produce infinities, regions forever hidden behind event horizons. If we swapped our Sun with a circumbinary planetary system's twin stars like Kepler-16, Earth would experience double sunrises and sunsets while orbiting both stars at once. Imagine two suns close together, one orange and one red, orbiting each other every 41 days while you orbit both at a distance, watching them spin round their mutual center like dancers, sometimes aligned so they eclipse each other, other times separated so shadows stretch in multiple directions at once, your year lasting 229 days around the binary pair. Kepler-16's stellar components were discovered in 2011 by NASA's Kepler spacecraft using the transit method, with masses of 0.69 and 0.20 solar masses, making the system much dimmer than our Sun even combined. The gravitational dynamics of circumbinary orbits create stability zones and exclusion zones where planets cannot exist, with stable orbits only possible beyond about 2 to 3 times the binary separation distance. Earth transported to such a system would need to be much farther from the stars to maintain stable orbit. But even at a distance yielding correct temperature, the strange lighting would fundamentally change how life perceives day, night, and seasons. This reminds us that planet formation occurs even in complex gravitational environments, that worlds can circle multiple stars, expanding the possible architectures for solar systems beyond what we see in our own. If we placed a yellow hypergiant-like row Cassiopeia where our sun sits, Earth would orbit a star so large and luminous it shouldn't exist. Imagine a sun 450 times wider than the one we know, pulsating irregularly, occasionally dimming for months as it ejects vast clouds of gas into space, shining 500,000 times more brightly but so far extended that its outer atmosphere is practically a vacuum, a star balanced on the knife edge between existence and self-destruction. Rho Cassiopeia sits about 8,200 light-years away in Cassiopeia, discovered to be variable by American astronomer Edward Charles Pickering in 1893. But its true nature as one of the rarest and most massive stars known emerged only with modern spectroscopy. In 2000, astronomers witnessed it eject a shell of gas equal to Earth's mass after its surface temperature dropped by 3000 Kelvin in just months, an event they called a hypergiant eruption. At our sun's distance, Earth would vaporize from the intense radiation while simultaneously being blown outward by the powerful stellar wind. The planet caught between competing forces of light, pressure, and gravity. To think that stars with masses 40 times our suns enter regions of the Hertzsprung-Russell diagram where they become unstable, inflating to grotesque size before dying young, shows us that nature has limits beyond which even stars cannot maintain composure. If we swapped our sun with a population 3 star from the early universe, Earth would orbit the first kind of star that ever existed. Imagine a sun made only of hydrogen and helium, no carbon, oxygen, iron, or any heavier element, burning at temperatures far higher than modern stars, living fast and brief, massive beyond anything we see today, shining blue-white with a harsh light that contains none of the spectral lines produced by metals. Population: 3 stars existed in the first few 100 million years after the Big Bang, when no elements heavier than lithium had been created yet. Theorized by astronomers Beatrice Tinsley and Richard Larson in the 1970s, but never directly observed because they died billions of years ago. These primordial giants probably ranged from 100 to 1,000 solar masses, living only a few million years before exploding as parent stability supernova that created the first heavy elements. If somehow transported to our current era at our sun's distance, such a star would be so hot and luminous that Earth would be heated above the boiling point of rock, vaporizing into a silicate vapor cloud. In a sense, these first stars were the furnaces that created every heavy atom in our bodies, that without their brief, violent lives and explosive deaths, planets and people would be impossible. If we replaced our sun with the exoplanet host star TRAPPIST-1, Earth would be one of 7 worlds huddled close around a dim red ember. Imagine a sun barely larger than Jupiter, cool enough that its surface temperature is only 2,500 Kelvin, glowing deep infrared red, so faint you could stare directly at it and only feel mild warmth on your face, while all 7 planets orbit closer than Mercury does to our sun. TRAPPIST-1 sits 40 light-years away in Aquarius, discovered in 1999, but its planetary system of 7 Earth-sized worlds wasn't revealed until 2017 by McCall Gillen and his team using the TRAPPIST telescope and confirmed by NASA's Spitzer Space Telescope. The star weighs only 9% of our sun's mass and produces merely 0.05% of its luminosity, meaning all 7 planets orbit within a sphere smaller than the distance from our sun to Mercury, yet some might have liquid water. Earth transplanted to this system would freeze at our current distance, requiring relocation to within 10 million kilometers of the star to receive adequate warmth, placing it closer to the star than any planet currently orbits our Sun. This reminds us that stellar mass dictates architecture, that around small stars, the habitable zone compresses inward, creating systems vastly different from our own, potentially common arrangements we're only beginning to discover. If we swapped our Sun with a gamma-ray burst progenitor in its final hours, Earth would orbit a massive star about to die in the most energetic explosion since the Big Bang. Imagine a Sun perhaps 30 times more massive than the one we know. Its core already collapsed into a black hole, but hidden beneath still burning outer layers. The star wobbling and pulsating as its interior rearranges itself. Jets of matter already drilling through the poles at nearly light speed, hours away from bursting. Gamma-ray bursts were first detected in 1967 by the VLA satellites designed to monitor nuclear test ban compliance. But their cosmic origin wasn't confirmed until 1997 when Beppo-Sayak's satellite localized one and revealed its incredible distance. The leading model, proposed by Stan Woosley, suggests long gamma-ray bursts come from collapsing massive stars whose cores form black holes while their rotation channels energy into twin jets. At our Sun's distance, Earth would be outside the narrowly focused jets that make gamma-ray bursts lethal across galaxies. But the precursor, supernova itself, would deliver enough radiation to vaporize the planet's surface. The neutrino flux alone depositing enough energy to heat Earth's core above its melting point. To think that somewhere in the universe this process happens once per day, that the cosmos routinely produces explosions releasing more energy in seconds than our Sun will emit in its entire 10 billion year lifetime. If we replaced our Sun with a millisecond pulsar like PSRJ 1748-24468, Earth would be spun and irradiated by the fastest rotating object known. Imagine a neutron star spinning 716 times every single second, its equator moving at nearly a quarter the speed of light. The beams of radiation sweeping across Earth's orbit like cosmic lighthouse beams, but at a rate too fast for human perception. Just a constant deadly glow of X-rays and gamma-rays. PSRJ 17482446 AD was discovered in 2004 by Jason Hessels, using the Green Bank telescope in a globular cluster 18,000 light-years away, rotating so fast it approaches the theoretical limit before centrifugal force tears neutron stars apart. The pulsar spins down by only 2.6 nanoseconds per year, meaning it will maintain this incredible rotation rate for billions of years. Its surface experiencing gravitational acceleration 100 billion times Earth's gravity. At our Sun's distance, the pulsar's rotation would create a pulsed radiation environment varying 716 times per second. The magnetic field inducing currents in any conducting material, including Earth's molten core and oceans, essentially turning our planet into a giant electromagnet. In a sense, millisecond pulsars represent matter's ultimate spin, the fastest possible rotation before physics says no more, the universe's natural speed limit made visible. If we swapped our Sun with Tabby's star, Earth would orbit the most mysteriously dimming star ever discovered. Imagine a Sun that occasionally and unpredictably dims by up to 22% over days or weeks, the brightness dropping far more than any planet transit could explain. The light curve showing asymmetric dips and patterns that don't repeat regularly, as if enormous structures were passing in front of the star in chaotic configurations. KIC 8,462,852, nicknamed Tabby's star after astronomer Tabitha Boyajian, who first reported its anomalous behavior in 2015 using Kepler Space Telescope data, sits 1,470 light-years away in Cygnus and has sparked intense scientific debate. Initial speculation ranged from megastructures built by advanced civilizations to swarms of comets, but current leading theories involve circumstellar dust or debris from a disrupted planet or moon. Earth orbiting this star would experience dramatic climate fluctuations as starlight intermittently decreased by amounts that would plunge temperatures by tens of degrees for weeks at a time, the unpredictability preventing life from adapting to any stable pattern. This reminds us that even in an era when we've catalogued billions of stars, individual objects can still completely surprise us, that the universe retains mysteries we haven't categorized. If we place the Thorn-Zitkow object where our Sun sits, Earth would orbit something that shouldn't exist, a neutron star hidden inside a red supergiant's envelope. Imagine a sun that appears normal, glowing red and enormous, but at its core, instead of fusion reactions, sits a city-sized ball of neutrons so dense that a sugar cube of its matter would weigh 100 million tons. The neutron star's gravity and heat driving the outer stellar layers through exotic nuclear reactions that create elements never found in normal stars. Thorn-Zitkow objects were theorized in 1975 by physicists Kip Thorne and Anna Zitkow as a possible outcome when a neutron star collides with or is captured by a supergiant star. Though the first candidate wasn't identified until 2014, when astronomers found HV 2112 in the Small Magellanic Cloud, showing unusual abundances of rubidium and molybdenum. The neutron core heats the surrounding stellar material to temperatures where exotic reactions create rapid process elements, normally made only in supernova. At our Sun's distance, Earth would experience temperatures similar to orbiting a normal red giant, freezing as the luminosity drops, but the stellar spectrum would be bizarre, showing element ratios that betray the hidden core. To think that stars can swallow neutron stars and continue shining illustrates how adaptable stellar evolution is. How many strange hybrid objects might exist? If we swapped our Sun with a zombie star like Tycho's supernova remnant's companion, Earth would orbit a star that survived its partner's explosive death. Imagine a Sun showing signs of trauma, its surface enriched with iron and nickel from supernova ejecta. One hemisphere possibly stripped by the blast wave, the star now alone where once a binary pair orbited, still burning but marked forever by catastrophe that vaporized its companion. Tycho's supernova in 1572 was observed by Danish astronomer Tycho Brahe and remained visible for 18 months. But only in 2004 did astronomers identify Tycho G as the possible surviving companion using the Subaru telescope to measure its unusual velocity of 136 kilometers per second through the remnant. Type Ia supernova are thought to occur when white dwarfs accrete matter from companion stars until they explode, sometimes leaving the donor star intact but traumatized. Earth orbiting such a survivor would experience higher radiation from the nearby supernova remnant, still expanding and glowing, while the star itself might have unstable fusion from its disrupted interior, making it variable and unpredictable. In a sense, this scenario shows us that stellar death affects whole neighborhoods, that nearby stars carry scars from explosions they witnessed, making them refugees fleeing cosmic violence. If we replaced our Sun with a circumstellar disk object like HL Tauri, Earth would orbit a proto-sun, still gathering material from its birth cloud. Imagine looking up to see, not a clear star, but a glowing disk of gas and dust-oriented edge on, gaps visible where protoplanets are clearing their orbits. the star itself occasionally obscured by clumps of falling material, the whole system glowing in infrared from friction heat as matter spirals inward, everything still in the process of becoming. HL Tauri sits 450 light-years away in Taurus and is less than 1 million years old, famous for the 2014 ALMA telescope image showing multiple concentric gaps in its disk, suggesting planets forming in real time. The disk extends over 100 astronomical units and contains several Earth masses of dust, along with hundreds of Jupiter masses of gas still falling toward the central star. Earth placed in this environment would be bombarded by protoplanetary debris, dust accumulating on the surface, while occasional kilometer-sized planetesimals impact with the energy of nuclear weapons, the entire sky obscured by the disk's glow. This reminds us that solar systems begin in chaos, that our current clear orbits and separated planets represent order emerging from primordial disorder. Billions of years of gravitational sorting. If we swapped our sun with a carbon-oxygen white dwarf accreting from a giant companion, Earth would orbit a system counting down to type Ia supernova. Imagine a tiny dense star slowly accumulating hydrogen onto its surface, the matter compressing and heating until it ignites in thermonuclear runaway. But instead of exploding immediately, the process gradually adds mass, each nova bringing the white dwarf closer to the Chandrasekhar limit of 1.4 solar masses when it will detonate completely. Recurrent novae, like RS Ophiuchi, undergo eruptions every 10 to 20 years as observed since 1898, with the white dwarf gaining net mass despite ejecting material in each outburst. Astronomers using Hubble have measured white dwarfs in some systems approaching the critical mass, making them supernova candidates within the next million years. Earth caught in such a system would be periodically swept by nova blast waves every decade or two, each eruption delivering weeks of intense ultraviolet and X-ray radiation that strips the ozone layer, while gravitationally the binary system's evolution might perturb planetary orbits over millennia. To think that we can identify stars that will definitely explode but can't predict exactly when reminds us that the universe operates on timescales where million-year uncertainties are precise, where patient violence brews. If we placed a Herbig, a B star like Ab Awaji, where our sun sits, Earth would orbit a young massive star surrounded by a spiral disk of gas and dust. Imagine a sun twice as massive and 10 times more luminous than the one we know, burning blue-white and hot, surrounded by a disk showing spiral arms and kinks that mark where a giant planet is forming, dragging material with its gravity, the whole disk glowing from the star's intense ultraviolet light, causing fluorescence. AB Awaji sits 531 light-years away in Auriga and is only 1 to 4 million years old. Discovered to have a spectacular disk by Hubble observations in the 1990s, with stunning spiral structure revealed by the Sphere instrument in 2020, suggesting a planet several times Jupiter's mass is forming. The disk contains complex organic molecules including cyanide compounds detected by radio telescopes, the chemistry of planet formation happening in real time. Earth in this system would be pelted by debris, the atmosphere thickened by constant micrometeorite infall, while the star's intense ultraviolet flux would strip lighter atmospheric gases and break down complex molecules faster than they could form. In a sense, watching these young systems is like seeing our own solar system's infancy preserved in amber, the processes that created our world still playing out around distant suns. If we swapped our sun with a circumnuclear star near Sagittarius A star like S2, Earth would experience gravity so intense that orbits become visibly relativistic. Imagine orbiting not a sun but a precise point of darkness, a supermassive black hole, your year lasting only 16 Earth years, your orbital speed reaching to 5% of light speed at closest approach, fast enough that relativistic effects become measurable, time running slightly slower for you, the star's light redshifted at periastron and blue-shifted at apostrophe. S2 was discovered in 1995 as part of Andrea Ghez and Reinhard Genzel's teams monitoring stars near the galactic center, with its 2018 periastron passage allowing the first detection of gravitational redshift in a star's light, confirming Einstein's general relativity in the strong field regime. The star weighs about 14 solar masses and approaches within 17 light holes of the black hole's event horizon at closest pass. Earth orbiting at 1 astronomical unit would experience tidal forces from the black hole, stretching it along the radial direction by meters, while the lack of light from the black hole itself would freeze the planet to -270 Celsius, just 3 degrees above absolute zero. This reminds us that nature creates gravitational environments so extreme they test our best physics theories, that space-time itself bends measurably around massive objects. If we replaced our Sun with V838 Monocerotis during its 2002 eruption, Earth would witness one of the most mysterious stellar outbursts ever recorded. Imagine a star suddenly brightening by 600,000 times over a few weeks, not from a nova or supernova but from an unknown process. The star swelling to become temporarily the largest star in the Milky Way, an expanding shell of light echoing outward, illuminating surrounding dust clouds in a cosmic light show. V838 Monocerotis sits 20,000 light-years away in Monoceros and erupted in January 2002, with Hubble capturing spectacular light echo images showing expanding rings of illumination spreading outward through previously invisible interstellar dust. Astronomers still debate the cause, with theories ranging from planetary consumption to stellar mergers, but no model perfectly explains the light curve and spectral evolution. At our Sun's distance, during peak luminosity, Earth would be heated above the melting point of lead, the temperature soaring to over 600 Celsius before the star cooled again within months. But the brief pulse might not completely vaporize oceans, creating a bizarre scenario where the planet is temporarily sterilized, then allowed to cool again. To think that stars can undergo eruptive events we still don't understand after centuries of astronomy humbles our knowledge, reminding us that the universe still teaches. If we swapped our Sun with a blue straggler star like one found in globular cluster 47 to Earth would orbit a star that appears impossibly young. Imagine a hot blue star burning brightly in a cluster where all similar stars should have died billions of years ago. Its existence defying stellar evolution theory, appearing perhaps 2 billion years old in a neighborhood that's 12 billion years old. A star that somehow reset its clock. Blue stragglers were discovered in 1953 by Alan Sandage while studying globular cluster M3. Stars that fall on the main sequence above the cluster turn-off point where normal stars have evolved into giants. Current theory suggests they form through stellar mergers when two smaller stars collide and combine their fuel, effectively creating a younger star, or through mass transfer in binary systems. At our Sun's distance, a blue straggler would shine perhaps twice as hot and several times more luminously than our Sun, heating Earth above the boiling point while flooding it with ultraviolet radiation. In a sense, blue stragglers are time travelers, stars given second lives through violent rejuvenation, their existence proving that stellar evolution isn't always a one-way path toward death, but can occasionally reverse through merger and rebirth. If we placed a Mira variable star like Mira itself where our Sun sits, Earth would experience light variations so extreme that brightness changes by a factor of 1,700 over 332 days. Imagine a sun that dims to barely visible even at noon, then over months brightens until it blazes too bright to comfortably watch. The temperature swinging from -100 to +50 Celsius with each cycle. Seasons becoming meaningless as the star's pulsations override any orbital effects. Mira in Cetus was discovered to be variable by Dutch astronomer David Fabricius in 1596, making it one of the first variable stars known. A red giant pulsating due to its outer layers expanding and contracting, driven by opacity changes in ionization zones. The star's variability results from it being near the end of its life, fusing helium in its core while hydrogen burns in a shell. The imbalance causing the 332-day pulsation cycle. Earth in such a system would be sterile, the climate chaos preventing any stable weather patterns or seasonal cycles that life requires. Frozen atmosphere condensing out during dim phase, then evaporating during bright phase. This reminds us that stellar stability is temporary, that all sun-like stars eventually enter unstable, pulsating phases before shedding their outer layers. A fate awaiting our own sun in its final billion years. If we swapped our sun with a white dwarf neutron star binary in close orbit, Earth would be caught between two compact remnants, spiraling together toward merger. Imagine two stellar corpses orbiting each other every few hours. One a white dwarf, the size of Earth, the other a neutron star, the size of a city. Gravitational waves carrying away orbital energy, causing them to slowly approach. Their mutual gravity raising tides on each other, the white dwarf stretched into an egg shape. Matter beginning to stream from the white dwarf toward the neutron star. Systems like PSRJ 1946 plus 3417 discovered in 2019 show white dwarfs orbiting millisecond pulsars with periods under an hour, some of the tightest binaries known. As the orbit decays, the neutron star's magnetic field channels accreted matter into hotspots, emitting X-rays, while gravitational wave emission accelerates the in-spiral toward eventual merger that might produce either a more massive neutron star or light black hole. Earth in such a system would orbit at a distance where gravity remains manageable, but would experience no sunlight, only the dim glow from the white dwarf and occasional X-ray flashes from accretion onto the neutron star, creating a frozen world illuminated only by exotic high-energy physics. To think that stellar remnants can orbit so closely they distort each other's shape illustrates how gravity sculpts even the densest matter. The dead stars engage in lethal dances. If we replaced our sun with a hypervelocity star ejected from the galactic center, Earth would be flung out of the Milky Way on an escape trajectory. Imagine a sun moving at 1,000 kilometers per second relative to the galaxy, fast enough to leave the Milky Way's gravity well entirely, carrying its planetary system with it into intergalactic space. The familiar spiral arms and dust lanes fading behind as you accelerate into the void between galaxies. Hypervelocity stars were first discovered in 2005 by Warren Brown using the MMT Observatory, with velocities exceeding the galaxy's escape velocity of 550 kilometers per second. The leading formation mechanism involves binary stars passing close to the supermassive black hole at the galactic center, where tidal forces tear the binary apart, ejecting one star at high speed while the other gets captured. Earth transported to such a scenario would still orbit its star normally. the gravitational binding within the solar system far stronger than galactic tides. But over millions of years, the stellar environment would change dramatically as we left the Milky Way's disk, the night sky gradually emptying of stars until only distant galaxies remained. In a sense, these stellar exiles show us that even stars can be refugees, that galactic centers are violent enough to fling entire solar systems into intergalactic space, creating lonely wanderers between the galaxies. If we swapped our sun with a protoplanetary disk gap carver like PDS-70's young stars, Earth would orbit in a cleared zone created by forming planets. Imagine a sun surrounded by a vast disk of gas and dust, but with your orbit lying in a swept clear gap. Walls of material rising on either side like cliffs. Young planets visible as bright spots in the disk, pulling gravitationally on the surrounding material. The star still accreting sporadically when clumps bridge the gap. PDS-70 sits 370 light-years away in Centaurus and is only 5.4 million years old. Famous as the first system where astronomers directly imaged planets still forming in the disk using VLT's Sphere instrument in 2018 and 2019, capturing PDS-70b and PDS-70c embedded in the disk. The gaps these planets carved are 2 to 3 billion kilometers wide, cleared as their gravity flings material either inward toward the star or outward. Earth, in such a gap, would experience far less meteorite bombardment than the early solar system endured, protected by the planet acting as gravitational shepherd. But the disk's inner edge would create a luminous wall in the sky, glowing from stellar radiation. This reminds us that planet formation is a tidy process, that growing worlds clean their neighborhoods, that gaps in disks are signposts reading a planet lives here. If we placed the magnetar SGR 1806-20 where our sun sits, Earth would experience the most violent magnetic environment possible. Imagine a neutron star with magnetic field strength reaching 200 billion Tesla, so intense that within 1,000 kilometers of the surface quantum electrodynamics predicts vacuum itself polarizes, becoming birefringent like a crystal, photons splitting into components based on their polarization orientation. SGR 1806-20 sits 50,000 light-years away and in December 2004 released a giant flare, the largest explosion observed in the galaxy in modern times, releasing more energy in 1/10 of a second than our sun emits in 150,000 years. The burst's gamma rays partially ionized Earth's upper atmosphere from across the galaxy, detected by multiple satellites as instruments went off-scale. At our sun's distance, the magnetar's normal emission would strip Earth's atmosphere while the magnetic field distorted atoms into needle shapes. But a giant flare at that range would be instantly lethal, delivering more radiation in milliseconds than standing on the surface of an exploding nuclear bomb. To think that neutron stars can store and suddenly release amounts of magnetic energy that dwarf stellar fusion output illustrates that magnetism can rival gravity and nuclear force in cosmic violence. If we swapped our sun with a red dwarf star in its active youth, like Proxima Centauri was for billion years ago, Earth would face relentless stellar tantrums. Imagine a sun that erupts in massive flares every few days, each one bright enough to temporarily double the star's total light output. The magnetic field lines twisting and snapping like cosmic whips, sending plasma bullets outward at thousands of kilometers per second. Young red dwarfs undergo what astronomers call a flare phase, lasting their first billion years. Discovered through observations of young stellar clusters like the Pleiades, where red dwarfs show activity levels hundreds of times higher than their older counterparts. Research published in 2018 by Meredith McGregor using ALMA telescope data showed that Proxima Centauri still flares violently despite being billions of years old, with flares increasing its brightness by factor of 10 for minutes at a time. Earth orbiting such an active star would have its magnetic field repeatedly compressed and breached, allowing radiation to reach the surface, sterilizing any emerging life, while ultraviolet photons broke apart water molecules in the upper atmosphere, hydrogen escaping to space. In a sense, red dwarfs make terrible hosts for life during their youth, their violence lasting longer than complex life took to evolve on Earth, suggesting habitable planets around such stars must wait patiently through eons of radiation bombardment. If we replaced our Sun with the quasar-like Blazer 3C 279, Earth would be aimed directly down the barrel of a relativistic jet. Imagine not just a bright object, but a focused beam of particles and radiation moving at 99.5% light speed, aimed by cosmic coincidence directly at your planet. The jet's synchrotron radiation spanning from radio waves through visible light to gamma rays. Blazars are active galactic nuclei whose jets point toward Earth, discovered as a class when astronomers realized some quasars showed extreme variability and polarization. 3C 279 sits 5.3 billion light years away in Virgo and varies in brightness by factors of 100 over timescales of days. Studied extensively since its identification by Caltech astronomer Martin Schmidt in 1959. The jet's particles, accelerated to relativistic speeds by magnetic fields near a supermassive black hole, create a searchlight effect where light is beamed forward and blue-shifted. At 1 astronomical unit from such an object, impossible though this scenario is, the jet would deliver radiation flux billions of times more intense than standing on the Sun's surface. Earth vaporizing into plasma in microseconds while the particle beam physically pushed against its remnants. This reminds us that supermassive black holes don't just pull matter in, but also launch some of it back out in jets that can affect entire galaxies. Cosmic particle accelerators of almost unimaginable power. If we swapped our Sun with a population to star like one from the galactic halo, Earth would orbit an ancient star from the universe's early generations. Imagine a Sun slightly cooler than the one we know but containing less than 1% of its heavy elements, formed when the galaxy was young from gas, barely enriched by earlier supernova, its spectrum showing almost pure hydrogen and helium with only traces of carbon, nitrogen, and oxygen. Population 2 stars were defined by astronomer Walter Baade in 1944 when he realized stars in globular clusters and the galactic halo showed different properties than disk stars like our Sun, older and metal poor. HD 140.283, nicknamed Methuselah star, is a population 2 subgiant located 190 light-years away and estimated by Howard Bond and colleagues in 2013 to be 14.5 billion years old, close to the universe's age of 13.8 billion years within measurement uncertainties. Earth orbiting such a star would receive similar light and heat since main sequence stars of similar mass shine comparably regardless of metallicity. But the protoplanetary disk that formed the solar system would have lacked heavy elements, possibly preventing rocky planet formation entirely. To think that the first generations of planets might have been impossible, that life required the universe to age and die and be reborn in supernova several times before worlds like Earth could condense, suggests we're products not just of our star, but of cosmic recycling spanning billions of years. If we replaced our Sun with Rs Ophiuchus recurrent nova system, Earth would experience thermonuclear detonations every 15 years. Imagine a white dwarf slowly pulling hydrogen from a red giant companion. The stolen matter accumulating on the white dwarf's surface in a layer that compresses and heats until it reaches 10 million Kelvin, then ignites all at once in a runaway fusion reaction, the entire surface exploding simultaneously, releasing in days the energy our sun emits in 10,000 years. Rs Ophiuchi has erupted in 1898, 1933, 1958, 1967, 1985, 2006, and 2021, making it one of the most frequently recurring novae known, each eruption studied in increasing detail as technology improved. The 2006 eruption was observed across the electromagnetic spectrum from radio to gamma rays, revealing shockwaves traveling at 5,000 kilometers per second through the red giant's stellar wind. Earth caught in this system would be periodically swept by the nova blast wave, receiving weeks of X-ray and gamma-ray bombardment strong enough to strip the ozone layer completely, creating mass extinctions every 15 years that reset any biological evolution that managed to begin. In a sense, recurrent novae show us that stellar death isn't always a one-time event but can be a repeating cycle. White dwarfs eating their companions, slowly detonating portions over and over like cosmic time bombs on a schedule. If we swapped our sun with a subdwarf B star in a post-Kármán envelope binary, Earth would orbit an exposed stellar core burning helium. Imagine a sun that skipped the red giant phase somehow, its outer layers stripped away to reveal the hot helium-burning core underneath, glowing blue-white at 30,000 Kelvin. Much hotter than normal main sequence stars, but surprisingly dim in total output. Subdwarf B stars form when red giants lose their hydrogen envelopes before helium flash, often through binary interaction where a companion strips away the outer layers. Discovered as a distinct population by astronomer Jesse Greenstein in the 1960s, the prototype HD 127,493 and thousands like it populate a region of the Hertzsprung-Russell diagram where no normal stellar evolution tracks pass. Earth around such a star would receive intense ultraviolet radiation despite the modest total luminosity. The UV flux thousands of times stronger than from our sun, ionizing the upper atmosphere and breaking apart ozone and oxygen molecules faster than they could reform. To think that stars can have their outer layers stolen by companions, revealing their cores prematurely, shows how binary evolution creates exotic objects impossible in isolation. That stellar evolution is far more complex when gravity entangles two stars together. If we replaced our sun with Fu Orionis during an outburst, Earth would watch a young star suddenly brighten by 100 times in months. Imagine a protostar, normally hidden in its cocoon of dust and gas, suddenly erupting, its accretion rate increasing dramatically as material from the surrounding disk dumps onto the star in an avalanche. The system brightening from invisible to naked eye visibility, then staying bright for decades or centuries before fading again. Fu Orionis itself erupted in 1936 and has remained about 100 times brighter than its pre-outburst state ever since, discovered by amateur astronomer Gusso and studied extensively because it remains accessible for observation. George Herbig proposed in 1966 that these outbursts result from thermal instabilities in the accretion disk, causing material to suddenly flow inward rapidly. Earth in such a system during quiescence would orbit a dim protostar barely adequate to prevent freezing, then during outburst be suddenly heated by 100 times more energy. Oceans boiling, atmosphere stripped by intense, stellar wind accompanying the accretion surge. This reminds us that star formation isn't smooth but punctuated by violent episodes, that protostars undergo growth spurts where they swallow decades worth of matter in years, their light flickering like candles in wind as they struggle toward stable fusion. If we swapped our Sun with a cataclysmic variable like SS Cygni, Earth would orbit a white dwarf and red dwarf locked in a vampiric relationship. Imagine two stars orbiting every 6.6 hours, close enough that the white dwarf's gravity pulls matter from its companion in a stream, the stolen gas forming a glowing accretion disk that spirals inward, periodically becoming unstable and erupting in dwarf nova outbursts every 40 to 60 days. SS Cygni was discovered to be variable in 1896 by Louisa Wells at Harvard College Observatory and has been monitored for over a century, brightening by factors of 10 to 100 irregularly but frequently. The dwarf nova outbursts occur when the accretion disk becomes thermally unstable, suddenly dumping large amounts of matter onto the white dwarf in days, releasing gravitational potential energy as visible light and X-rays. Earth in this binary system would experience complicated gravitational perturbations from two stellar masses orbiting each other, while the periodic outbursts would subject the planet to pulses of X-ray radiation every month or two, creating a bizarre environment where radiation storms are predictable events. To think that in death, stars can become more active than they were in life, that white dwarfs can outshine the main sequence stars they evolved from by stealing their neighbors' matter, illustrates how endings are often just transitions to new behaviors. If we replaced our Sun with a B star like Acrona spinning near breakup velocity, Earth would orbit a star so flattened by rotation it looks like a cosmic pancake. Imagine a Sun rotating once every few days, spinning so fast that centrifugal force at the equator nearly balances gravity. The star's shape distorted from spherical into an oblate ellipsoid with equatorial diameter 50% larger than polar diameter. Matter occasionally flung off the equator into a disk. Acherna in Eridanus is the flattest star measured, with observations published in 2003 by Pierre Cavella using ESO's VLTI interferometer, revealing its equator bulges outward, making it 1.5 times wider than its pole-to-pole distance. B stars rotate at 80 to 90% of their critical breakup velocity and are surrounded by decretion, disks of matter they've flung off, detected through hydrogen emission lines, hence the E designation. Earth orbiting such a star would receive different amounts of light depending on viewing angle, more from the poles where the surface is hotter and less from the cooler equator, creating bizarre seasonal variations as orbital inclination determines which view we get. In a sense, these stars are cosmic spinning tops pushed to their limit, their rotation a visible reminder that angular momentum shapes celestial objects just as much as gravity does. If we swapped our Sun with a symbiotic nova like V407 Cygni, Earth would orbit a white dwarf embedded in a red giant's wind. Imagine a tiny dead star plowing through the atmosphere of a giant companion, surrounded by a cocoon of dense wind material, occasionally erupting in nova explosions whose blast waves collide with the giants, wind creating shock fronts that accelerate particles to relativistic energies. V407 Cygni erupted in March 2010, discovered by Japanese amateur astronomer Koichi Nishiyama, and became the first nova detected in gamma rays by NASA's Fermi telescope. The gamma ray emission comes from protons accelerated to nearly light speed in shocks where the nova ejector, moving at 4,000 kilometers per second, crashes into the red giant's wind. a process previously thought to occur only in supernova remnants. Earth in this system would orbit within or near the red giant's extended wind, experiencing increased atmospheric drag from tenuous gas, while periodic nova eruptions would deliver radiation and energetic particles, the gamma rays penetrating deep into the atmosphere and potentially affecting climate through ionization of the lower stratosphere. This reminds us that stellar winds aren't empty space, but material environments with consequences. That matter shed by one star becomes the medium through which another's explosions propagate, creating physics laboratories impossible to recreate on Earth. If we replaced our Sun with a protostar like HOPS 383, still deep in its birth cloud, Earth would orbit blind. Imagine a sun completely hidden inside a cocoon of dust, so thick that visible light cannot escape. Only infrared radiation leaking out, your sky utterly black in visible wavelengths, but glowing warmly in infrared. The star's heat radiating through dust that absorbs and re-emits it at longer wavelengths. HOPS 383 in the Orion Nebula is a deeply embedded Class 0 protostar discovered in infrared surveys, still accumulating matter from its collapsing cloud core, with most of its mass still in the surrounding envelope rather than the central object. Such protostars are detectable only in 4 infrared and submillimeter wavelengths, because extinction by dust exceeds 100 magnitudes in visible light, meaning for every trillion photons emitted, only one escapes. Earth transported to such an environment would be immersed in the dense molecular cloud, the sky-black atmosphere snowing with organic molecules and ice-coated dust grains, temperature determined by the infrared glow rather than direct starlight. To think that all stars begin this way, including our Sun, that there was a time when our solar system was invisible to any external observer, makes us realize birth is often hidden, that beginnings happen in darkness before breaking into light. If we swapped our Sun with a helium star like the companion in the Cygnus X1 system stripped by the black hole, Earth would orbit a star missing its entire outer layer. Imagine a sun with no hydrogen envelope at all, its surface exposed helium and heavier elements, burning at temperatures of 80,000 Kelvin, glowing intensely blue, far hotter than any main sequence star. Its evolution accelerated because it's burning helium directly in what should be its outer layers. Helium stars form when massive stars in close binaries have their hydrogen envelopes stripped by companions before they can evolve naturally into red supergiants. Discovered as a theoretical class in the 1970s and confirmed observationally in systems like Cygnus X1, where an O-type star feeds a black hole. These stripped stars evolve quickly, living perhaps a few 100,000 years before exploding as type IB or IC supernova. Earth around such a star would be bathed in extreme ultraviolet radiation, the stellar wind carrying little hydrogen but rich in helium and heavier elements, creating a bizarre chemical environment where the rain and atmosphere contain alien abundance ratios. In a sense, helium stars are dissected stars, their layers peeled away to expose interiors that should remain hidden. Stellar anatomy made visible through gravitational violence. If we replaced our Sun with the hypothetical quasi-star theorized to exist in the early universe, Earth would orbit a star with a black hole at its center. Imagine a sun so massive that its core collapsed into a black hole while the outer layers continued burning. A cosmic matryoshka doll with a stellar mass black hole nested inside a giant envelope of fusing hydrogen. The system shining with millions of times our Sun's luminosity from accretion onto the central black hole. Quasistars were proposed by theorists Begelman, Ollanteri, and Rees in 2006 as a formation pathway for supermassive black holes in the early universe, requiring extremely dense primordial gas clouds to form. These objects would reach 10,000 solar masses and shine for perhaps 1 million years before the envelope disperses, leaving behind intermediate mass black holes that could serve as seeds for later supermassive black holes. At our sun's distance, a quasistar would deliver radiation intense enough to melt Earth's surface, while gravitational perturbations from the massive system might disrupt planetary orbits entirely. To think that black holes might form not just from stellar death, but sometimes inside still living stars, as parasites consuming their hosts from within, suggests formation pathways we're only beginning to imagine. If we swapped our sun with a massive binary on the verge of merger like HD 93206, Earth would orbit two giants spiraling together in their final dance. Imagine twin suns, each 30 times more massive than the one we know, orbiting so close they complete a circuit every few days, tidal forces distorting both stars into teardrop shapes, stellar wind from each star colliding at a shock front between them that glows in X-rays. HD 93206. In the Carina Nebula is an O-type binary with components so massive and close that they'll merge within a few million years, discovered through spectroscopic observations that revealed two sets of absorption lines periodically shifting. Such massive binaries evolve quickly, with both stars burning through their fuel and expanding, eventually making contact and beginning mass exchange. Earth in this system would experience complex variations in light and heat as the binary orbit presents different configurations, while the X-ray emission from colliding winds irradiates everything, and gravitational perturbations from two massive stars orbiting nearby might destabilize planetary orbits over thousands of years. This reminds us that in crowded stellar environments, isolation is rare, that most massive stars form in multiples and their evolution becomes a shared story of mutual influence and eventual merger. If we replaced our sun with a luminous red nova progenitor like the stars that formed V838, Monocerotis, Earth would orbit on the eve of a stellar merger. Imagine two stars orbiting inside a shared envelope of gas, friction slowing their orbit, the two cores spiraling closer, year by year, the system appearing as a single red giant, but actually containing two objects about to collide and merge, their combined light about to surge in an eruption lasting months. Luminous red novae were recognized as a distinct class of transient in the 2000s, dimmer than supernova but brighter than classical novae, with light curves and spectra suggesting stellar mergers. V1309. Scorpio provided the smoking gun in 2008 when astronomers realized archival data showed it as a contact binary that gradually merged, the light curve documenting the entire in-spiral process leading to eruption. Earth around such a system would experience gradually increasing tidal effects as the binary orbit decays, but the merger itself would be catastrophic, heating the planet to thousands of degrees for weeks as luminosity surges, potentially vaporizing the entire surface. To think that some stellar brightening events we observe are actually mergers in progress, two stars becoming one in a cosmic collision, reveals that even stars aren't permanent individuals but can combine and transform. If we swapped our sun with an AM Canum Venaticorum binary, Earth would orbit two white dwarfs, transferring helium between each other every few minutes. Imagine two dead stars, each the size of Earth but far more massive, orbiting so close they complete a circuit in 17 minutes, one stealing helium directly from the other's surface via Roche lobe overflow, the shortest orbital period binary systems known. AM Canum Vanatocarum itself was discovered to have a 17.1-minute period in 1967, with subsequent observations revealing its spectrum shows only helium lines, no hydrogen at all. These systems form when both stars lose their hydrogen envelopes through earlier mass transfer episodes, leaving pure helium white dwarfs that continue transferring matter. Earth in such a system would receive no significant light, only the dim thermal glow from two cooling stellar remnants, freezing to near absolute zero, while gravitational wave emission causes the binary to spiral inward, destined to merge within millions of years into a single more massive white dwarf, or possibly detonate as a peculiar supernova. In a sense, these systems represent stellar relationships taken to the extreme. Two corpses locked so close that they cannot be separated, sharing their substance in perpetual exchange as they die together. If we swapped our Sun with a circumbinary planet host like Kepler-47's twin stars, Earth would orbit two suns while watching multiple other planets do the same dance. Imagine looking up to see an orange dwarf and a red dwarf locked in orbital embrace, circling each other every 7.5 days, while you and at least two other planets circle both stars at various distances, creating a gravitational ballet of extraordinary complexity. Kepler-47 sits 3,400 light-years away in Cygnus and was discovered in 2012 by Jerome Oresh and colleagues using NASA's Kepler spacecraft, revealing at least 3 planets orbiting the binary with periods ranging from 49 to 303 days. The system's stability requires planets to orbit far enough that the binary appears as a single gravitational source, typically beyond 3 times the binary separation distance. Earth placed in the habitable zone of such a system would experience double sunrises, where the stars rise together or separately depending on orbital phase, shadows cast in multiple directions, and seasons determined by both the planet's orbit around the binary and the binary's own evolution. This reminds us that planetary systems need not be simple, that worlds can circle multiple suns, creating environments of bewildering complexity, expanding the possible homes for life beyond our sun-centered assumptions. If we replaced our Sun with a lithium-rich giant like TYC 429-20971, Earth would orbit a star exhibiting chemistry that shouldn't exist. Imagine a red giant whose spectrum shows lithium absorption lines far stronger than theory predicts, containing 3,000 times more lithium than similar stars, as if the star somehow created or preserved this fragile element despite interior temperatures that should destroy it. Lithium-rich giants were first recognized as anomalous in the 1980s, with TYC 429-20971 discovered in 2018 by Chinese astronomers to have the highest lithium content ever measured in a giant star. Lithium normally gets burned at temperatures above 2.5 million Kelvin, meaning any lithium in a star's convective envelope should be transported downward and destroyed, yet some giants show fresh lithium, possibly from recent planet consumption or some unknown internal production mechanism. Earth orbiting such a star would receive normal red giant illumination, likely freezing as the luminosity proves insufficient at habitable distances. But the real mystery is cosmological. Why does this star violate our understanding of stellar mixing and nucleosynthesis? To think that even stellar chemistry can surprise us, that some stars break the rules we thought governed element creation and destruction, suggests stellar interiors remain incompletely understood despite a century of nuclear astrophysics. If we swapped our Sun with an extreme horizontal branch star like Barnard 29, Earth would orbit a star burning helium in its core while weighing less than half our sun's mass. Imagine a sun that lost most of its hydrogen envelope somehow, now exposed down to its helium-burning core, shining hot and blue at 35,000 Kelvin but surprisingly dim in total output. A stripped-down star revealing its nuclear furnace directly. Extreme horizontal branch stars populate globular clusters and were discovered as a distinct population by Alan Sandage in the 1950s. Stars that somehow shed their outer layers before or during helium flash, possibly through binary interactions or extreme mass loss on the red giant branch. Barnard 29 in the globular cluster M13 is a classic example. Burning helium to carbon and oxygen at its core, with only a thin hydrogen shell remaining. Earth around such a star would be flooded with ultraviolet radiation despite modest visible light levels. The UV flux intense enough to photodissociate water vapor and drive atmospheric escape. In a sense, these stars are evolutionary shortcuts. Having skipped most of the red giant phase 2, reveal their cores prematurely, showing us what our sun's interior will look like billions of years from now, but externally visible today. If we replaced our sun with a post-asymptotic giant branch star like HD 233517, Earth would orbit a star rushing between giant and white dwarf phases. Imagine a sun that recently shed its outer layers as a planetary nebula but hasn't yet settled down as a white dwarf, still shining with 1,000 times our sun's luminosity from stored thermal energy, its surface temperature rising rapidly as layers contract. The star crossing the Hertzsprung-Russell diagram horizontally at speeds covering in decades what most stellar evolution takes millions of years. Post-AGB stars were recognized as a class in the 1980s when infrared surveys discovered luminous cool stars with evidence of recent mass loss, spending perhaps 10,000 years in this transitional phase. HD 233517 shows dusty circumstellar material from its recent mass loss and spectral lines indicating temperatures rising from 6,000 to over 30,000 Kelvin as it contracts. Earth orbiting during this phase would experience rapidly changing conditions, temperature rising as the star heats up while luminosity stays high. A brief window of intense illumination before the star fades to white dwarf status. This reminds us that stellar evolution isn't always slow, that transitions between phases can be rapid, that stars occasionally sprint through transformations that usually unfold at glacial pace. If we swapped our sun with a gamma-ray binary, like PSRB 1259-263, Earth would be caught between a pulsar and a massive star exchanging energy through their winds. Imagine a neutron star orbiting a B star every 3.4 years in an eccentric orbit. The pulsar's relativistic wind colliding with the massive star's equatorial disk twice per orbit. The collision region shining in X-rays and gamma rays as particles accelerate to extreme energies in the shock fronts. PSRB 1259-63 was discovered as a radio pulsar in 1992, but its gamma-ray emission wasn't detected until 2011 by Fermi and Hess telescopes, revealing that these wind collisions create natural particle accelerators rivaling anything humans can build. The system brightens dramatically in high-energy radiation around periastron when the pulsar plows through the B star's disk, with emissions lasting weeks as the shock wave processes material. Earth in such a system would orbit at a safe distance but would be periodically bathed in X-rays and gamma rays during periastron passages, creating radiation storms every 3.4 years intense, enough to affect atmospheric chemistry and potentially create mass extinction events. To To think that binary stars can create environments where particle physics experiments play out on astronomical scales, where stellar winds serve as cosmic laboratories for extreme acceleration, shows how binary evolution creates exotic phenomena impossible in isolated stars. If we replaced our Sun with a Thorn-Kitkow object candidate like HV 2112 in the Small Magellanic Cloud, Earth would orbit a star that might contain a neutron star core. Imagine a sun that appears externally as a cool red supergiant, but if theories are correct, harbors at its center a neutron star rather than a normal fusing core. The boundary between normal stellar plasma and neutron degenerate matter hidden deep within. Exotic nuclear reactions, creating element abundances never seen in normal stars. HV 2112 was identified in 2014 by Emily Levesque and colleagues who noticed its spectrum showed unusual excesses of rubidium, lithium, and molybdenum, elements theorized to form in the high-temperature environment surrounding a neutron core. Thorn-Kitkow objects remain hypothetical, with formation requiring a neutron star to survive being captured by or merging with a supergiant's envelope without being destroyed. Earth orbiting such an object would experience conditions similar to orbiting a normal red supergiant, likely freezing at habitable distances, but the star's nucleosynthesis would be bizarre, potentially enriching any planets with elements rare elsewhere. In a sense, if these objects exist, they represent stellar Russian nesting dolls. One complete dead star existing inside another living one, a configuration so exotic that even confirming one exists remains controversial. If we swapped our Sun with a supernova imposter like Eta Carini during its 1840s eruption, Earth would watch a star nearly destroy itself without actually exploding. Imagine a sun suddenly brightening to rival Sirius, despite being 7,500 light-years away, ejecting matter equal to 10 Earth masses over a few years, creating an expanding nebula called the homunculus visible today through telescopes, the star dimming afterward but surviving, having shed outer layers through a mechanism still not fully understood. Eta Carini's great eruption from 1837 to 1856 made it temporarily the second brightest star in the sky. Studied extensively by John Herschel, who documented its light curve from South Africa. Modern observations reveal the homunculus nebula expanding at 650 kilometers per second, containing nitrogen-rich material, suggesting the eruption exposed layers processed by CNO cycle fusion. Earth at 1 astronomical unit during such an eruption would be subjected to a blizzard of stellar material. The planet's atmosphere compressed by ram pressure from the ejector moving at hundreds of kilometers per second. Surface heated to thousands of degrees by the increased luminosity. Sterilization occurring over months as the outburst continued. To think that stars can undergo eruptions rivaling supernova in energy output, yet survive intact, suggests mass loss mechanisms we're still discovering, that stellar death has more variations than our models initially predicted. If we replaced our Sun with a carbon-enhanced metal poor star like He 010752440, Earth would orbit one of the most ancient stars in the galaxy. Imagine a sun formed when the universe was less than 1 billion years old, its atmosphere containing only 100,000th the iron content of our Sun, but strangely enriched in carbon, perhaps polluted by a single nearby supernova in the early universe, a chemical fossil preserving information about the first stellar generations. He 010752440 was discovered in 2002 by Norbert Christlieb and colleagues during the Hamburg ESO survey, with follow-up spectroscopy revealing iron abundance 200,000 times lower than solar, but carbon only 25 times lower. These carbon-enhanced metal-poor stars likely formed from gas clouds, enriched by faint supernova or perinstability supernova from very massive population 3 stars. Earth orbiting such a star would receive similar light and warmth, since main sequence properties depend mainly on mass. But any protoplanetary disk would lack the heavy elements needed to build rocky planets, possibly containing only ices and carbon compounds. In a sense, these stars are time capsules, their atmospheres preserving the chemical signature of the universe's first few 100 million years, allowing us to read cosmic history in their spectra. If we swapped our Sun with a BE supergiant like LHA 115S18 in the Large Magellanic Cloud, Earth would orbit a massive star surrounded by a dusty disk, despite being far evolved. Imagine a blue supergiant, normally expected to have powerful spherical stellar winds, instead showing forbidden emission lines in its spectrum indicating dense equatorial disk, the star rotating rapidly and possibly in a binary system that confines ejecta into a disk rather than allowing spherical expansion. BE supergiants were recognized as a distinct class in 1976 by Roberto Mendes and Verpi Niemela, when they noticed some early type supergiants showed forbidden emission lines normally seen only in low-density nebulae. LHA 115S18 shows evidence for a dense, dusty disk containing silicates and complex organic molecules, unusual for such a hot, massive star. Earth in such a system might actually orbit within or near the equatorial disk, experiencing increased dust accumulation in the upper atmosphere while the star's 20,000 Kelvin temperature delivers intense ultraviolet radiation. This reminds us that even massive stars can have complex geometries, that stellar winds need not be spherical, that rotation and binarity create structures around stars that challenge simple evolutionary models. If we replaced our Sun with a yellow supergiant like Polaris during its instability phase, Earth would orbit the North Star itself, experiencing pulsations that vary its brightness. Imagine a Sun 5 times more massive than the one we know, but evolved into a swollen supergiant phase, pulsating with a 4-day period as its outer layers expand and contract, driven by opacity variations in its ionization zones.